Okay, test, are you live? Test, test.
Rush you through this a little bit. We'll talk about it together.
Does anybody have the live stream on? Do we have audio on the stream? We do. Cool. All right. Good morning, everyone. Welcome to Monday. What is today? The 12th, 13th? 12th of July. We're flying through the semester and we're ready for another midterm already a week from today. My goodness. Lily and you are going to review tonight. I think there's a review session tonight. A couple of the UGSIs are going to go over the last midterm questions for you. So that's online. You can see the announcement on the website. We were talking about the properties of waves, and we're starting to understand them quite well now. And I'm going to show you a demo here first off, but let me set this up. So we saw last time that if you have a wave pattern impingent, is a big word, striking, let's just say if you point a laser at two slits, then we have this language barrier thing. There's a lot of new words you have, and then maybe I use crazy vocabulary, and then there's the accents and the a lot of people watching from all around the world, and we have, of course, a lot of accents in the class. Leo's Canadian, can't understand a word he says. So I'll try to use the simplest form of the language I can. So a laser shining at two slits passes through, and instead of seeing an image of the slits, a bright spot here and a bright spot here, we see this diffraction pattern. And the diffraction pattern we understand now is coming from the fact that the waves, and I'll draw that on there. Not very good with the artwork, but wave property is here. So when a wave from the upper slit, I have to make it. When a wave from the upper slit hits this spot, coming from the lower slit, this path is longer. So when I come from the lower slit, see if I can make it work. When I get here, I'm at a down part of the wave on this one and an up part of the wave on that one. And those right here cancel out. That's destructive interference. A wave coming at a high and another one from the other slit at the same time coming at a low cancel each other out. That's destructive interference. And of course, right in the center, that's constructive interference because they both have the same path to get there. So we looked at that, and we looked at a chem quiz, and we'll run a quick demo here on the screen. And what we're going to try to do, we have something new today. We're going to try to switch the feed to just the just this. So you can't see me anymore. You can just see the tablet. And hopefully, anybody watching the live stream, does that look good on the live stream? So you just see the tablet interface. So you can just listen to me now, but this is now a red light source coming onto a screen, and we can, what we notice is bright and dark spots. So if I annotate, you can see bright spot, dark spot. So those are coming from, now we understand the waves. And what I have here is them spread out kind of infinitely. But if there's also diffraction, so this is interference. We call interference the waves adding constructively or destructively. That's called interference, the waves interfering with each other. There's also the property of diffraction, and you can overlay that on top. So here's the diffraction pattern, which is that dotted line. And if you have just the if you have the interference and the diffraction acting together, then the bright and dark spots fade as you get farther from the screen. And in this animation, you can do what we did last time we said you have a wavelength of red light. Say you increase the wavelength, and you can see as I increase the wavelength to blue that those lines get closer together. So you can see the position of the peaks and the troughs, the bright spots and the dark spots change as the wavelength change. And we did a chem quiz on that. And we understand now it's just due to the interference, the waves traveling different path lengths and different wavelength. You'll have a different place where they interfere and constructively and destructively. So we'll go back to our board, and you can switch the camera back to me. So what we have here is a intensity, and we're also associating that with probability. So now we know that the light has a particulate nature. So it comes in packages we call photons. So this associating the intensity with the probability starts to make more sense. Well, if it's coming in packages, this is the probability that those packets, those pellets, those particles are hitting right in the center. High probability, high intensity. Low probability, low intensity. So low probability of photons striking there, high probability of them striking here. So let's go to where we left off last time, which was here. And we were going to look at that particulate nature of light a little more carefully. So what we have is the situation where electromagnetic waves are striking a metal. And on a metal, there are electrons, and we know they're relatively loosely attached to their atoms. The electrons can move about the bulk of the metal. They can move about the material, essentially from atom to atom. And that's what allows metal to conduct electricity. So you can get the electrons to move along. So there's this idea that they're held there by the attractive forces, but they can be jostled and moved. So what you notice, what happens is, if you shine light on many metals, laser light, we know that that alternating electric field can cause the electrons to move. We've seen that. And let's look at the demo one more time. Lillian, you're the pro on this. Can I ask you to help me with the demo? Now, we're going to do something nutty here. So you might be able to pan out the shot. You might not have to. See what it looks like with Lillian and I. Let's turn our waveform over and then just pull really tight. I'll pull tight against you. How does that look in the shot? Good. So we saw that when waves travel through space, they have this, if we get them oscillating high enough, we get electromagnetic radiation. So high frequency gives us this electromagnetic radiation, and that propagates through space as if it's rippling the space. And we saw that if you have an object, so say I'm oscillating a charge here, I can affect an object there. So oscillating plus minus, I can make the ducky bounce at a distance. It reacts to the moving space. And I can have a big bounce, that's a long wavelength, or short wavelength, and it responds appropriately. So I can have high amplitude, high intensity, or I can have high frequency and have the ducky react. That's enough of the ducky anyway. So thank you, Lillian. For those of you guys that don't get to see Lillian, she's not your particular UGSI. That's a treat for everyone. So here's the issue, though. Some wavelengths eject electrons from the metal, and some wavelengths don't. what are the properties of the light that make electrons eject from the metal? So you can imagine you get the electron moving, but you give it so much more kinetic energy, it leaves the metal altogether. So what properties would do that? And when we're looking at the stretched cloth here, we are at the understanding of about 1928, where the idea that light traveled as a wave was being explored and codified, mathematically understood. And it was quite readily understood light behaved as a wave. So then you look at the photoelectric effect and you say, well, how do I get the electrons to come flying off? Well, I think you would say, I was standing there and flopping that to get the electrons to come off. You would think high amplitude, high intensity would bounce that electron off, give it the most possible kinetic energy. And you would be correct in 1928. Well, you never be correct because that's not what happens. That turns out not to work. You'd think and everybody in 1928 is going, they've all got their duckies. I'm sure that Einstein had a cloth and ducky, and he was doing this. The higher amplitude, you'd think you could launch the electron out, but higher amplitude doesn't work. Higher amplitude means more intensity. If you turn up the brightness, so you make this red light very bright, and it doesn't help you. Dim doesn't work. Bright doesn't help. So we were at a conundrum in 1928. If you went to higher wavelengths, you could get an electron to come off. I said higher. I meant shorter wavelength. Went to shorter wavelength, higher frequency, then you could get an electron to jump off. So long wavelength doesn't do anything, no matter how bright you get it. But as soon as you get to green, higher frequency, shorter wavelength, electrons start coming off. So that's strange. So that's, rather than doing this high amplitude, you go to higher frequency. And for some reason, higher frequency makes the electron jump off. So that was not well understood. So I'm going to go to even higher frequency, shorter wavelength, and electron jumps off with more kinetic energy. You can measure the current. You can measure the electrons, the free kinetic energy of the electrons. So not particularly well understood. And even right now in our understanding, we're not exactly sure what's going on. But here's what it is. It turns out Einstein did understand this, and he did explain this, and that's what he won the Nobel Prize for his paper on the photoelectric effect, the photoelectric nature of metals and light. So he did all that work, of course, later in relativity and gravitation that he's so well known for, but the Nobel Prize came for explaining this. So what it looked like was, to Einstein, and we've seen this, so we already know this, the electron is trapped in a low energy situation. To get it out of that situation, you have to give it enough energy, enough kinetic energy to exceed that well. So we call the depth of the well here capital psi. Sometimes you'll hear it called the work function. That's in the literature, but it's the amount of energy you need just to get away from the metal, just to get out of that barrier. For some reason, red doesn't do it, green does, and blue does, and then this excess energy becomes kinetic energy. And this Einstein was able to understand because he said, it's the particulate nature. It turns out this other guy, Max Planck, at the same time had postulated that light had a particulate nature to it. Planck's constant, he said E equals h nu. And Einstein said, this looks like what's happening is the particles of light have to hit an electron and knock them out. So if you have a red, that photon is low energy, and it doesn't knock the electron out. It hits it, but it doesn't knock it out because it doesn't transfer enough kinetic energy. But the higher energy, green, each photon has higher energy. So it hits them harder. And blue hits them even harder. So the idea, the particulate nature of light, we have this diffraction and interference experiment that beautifully shows the wave nature of light. The particulate nature of light is beautifully shown here. So you can plot, and I love you, I know you love it when I do this. So if you plot the kinetic energy of the electrons coming off versus the frequency, the energy increasing here, frequency of the light on the metal, you will get a straight line. And we already kind of understand this. So we understand that for some low frequencies, the electrons aren't ejected at all. And then you'll get to a frequency where there's enough energy in the photons to excite them. And then as you go to higher frequencies, you eject them and you give them more kinetic energy. So you can plot that out quite beautifully. And let's say this is one specific metal, metal 1. This minimum frequency that just gets the electron off the metal, we'll call nu naught, 0. That's just what you need. All the rest of the energy, if there is any, goes into kinetic energy. So this is the amount of energy needed to ionize, to get that electron off the metal. If you go to higher frequencies, you would get higher kinetic energy for this metal, but metals are different. So here's metal number 2, a plot for metal number 2. This one holds its electrons more tightly because it takes more energy. A blue photon, higher frequency, shorter wavelength to eject there. So basically, we know the energy of the photons equals h nu, Planck's constant, named after Planck. The kinetic energy the electron has is the energy of the photon minus this amount of energy that's holding on to it. So all the rest of the energy goes into kinetic energy. So if you give it energies less than this, then it doesn't have any kinetic energy. No such thing as negative kinetic energy. But if you give this photon is bigger than this, then you have some kinetic energy. And you can see it's a straight line. Y equals mx plus b. The slope is Planck's constant. So that's a lovely experiment. And it's funny, not many people know this. Very few people know the actual origin. So Einstein figured this out. He and Max Planck were friends, and they would go to the junkyard on the weekends, and they were kind of degenerates. They would break glass windows, all the stuff on the old cars and stuff. They would throw rocks and just break windows. So Einstein, among his many inventions, was the pea shooter. You guys know what a pea shooter is? That's where you take like a straw and you can shoot a pea or a little BB out of it. So Einstein was thinking, if I could make an auto pea shooter, I could really, like rapid fire automatic weapon, break some windows. So he got it set up so that it didn't go through his mouth, but he would be able to shoot just a spray of the particles. So he goes down excited with Max Planck, and he goes, watch this. And he starts shooting his particle beam, his spray of particle at the glass window, but it doesn't break it. And he goes, why doesn't it break? I'm shooting a lot of particles at it. And Max Planck picks up a big rock and he says, well, I can break it, and he throws the big rock at it, and it smashes. One big rock, a lot of little particles. The big rock had that high kinetic energy. That's the big bang, smash, you break the window. If your rocks are little, it doesn't matter how many hit, because it's the individual pebble that has to break it. So if you go to high intensity, if one doesn't break it, bing, then 1,000 aren't going to break it per second either. So high intensity does not work. You need the individual energy in each photon. Throw the rock, not the pea shooter. And of course, Einstein, as soon as he realized that, he goes, oh my God, like, oh my God, I understand the photoelectric effect. That's what's going on. I'm going brighter, you're going higher energy. You're breaking it. Oh my God, oh my God, oh my God, I think I understand. And then he's thinking, Nobel Prize, Nobel Prize, Nobel Prize. Oh, I'm so excited. Oh, I almost peed a little. Okay. None of that happened. You'll not find it in the history book because I made that all up. But it's illustrative of the actual effect. So I can write both of these energies, h nu. Oops. I can write both of them in terms of a photon energy. So I can say the energy coming in on the photon, you subtract away this minimum amount, and written in terms of a photon energy instead of the work function. It's just an energy, it's just a number of joules. That is the plot that you see there. This one is a constant, h nu naught. This you could vary, change that, and then that would move the frequency along that axis. So let me ask you this. Shining a beam of light on a certain metal has no effect. What change would most likely get to eject electrons? We'll go through this one together. So we've already said, if you have a wave coming in and it's not ejecting electrons, you know, making it brighter, more intense, more BBs per second, more photons per second is making things brighter, more intense, higher amplitude. This is a lot of photons per second, but it doesn't mean the photons individual have more energy. You need the high energy photons. If you have high energy and high amplitude, then you eject more electrons because it's the individual particles on the wave that are ejecting the electrons. More at the same kinetic energy, just more of them. So we know in order to do this, you have to increase the energy packets, the energy of the photons. You would do that by increasing the frequency or decreasing the wavelength. So those are actually both there. So I have to get a photon. Here's E equals h nu. You can also write it as E equals hc over lambda. Remember, lambda times nu is the speed. So wherever I see a nu, I could put a c over lambda in. So that gives you the relationship between the wavelength and the energy. But to get more energy, I have to decrease the wavelength, inversely proportional. But both of those are there. So increase energy and decrease wavelength are both correct here. So I go to, from yellow, I should go up to red or green or blue, higher frequency to get that to electron to eject. This one you can do, let's do in our breakout rooms. So here we're plotting the kinetic energy of electrons coming off the metal. So these are photoelectrons, we call them, electrons flying off the metal. Here's the energies that they have for metal number 1 and metal number 2 plotted against the energy of the photons coming in. So the question is, which combination of photons striking the metal ejects an electron with the highest kinetic energy. So we have 3 possible photons, 2 possible metals. Which combination among these is the highest in kinetic energy? Think about that for a second. Talk amongst yourselves. I'll start the machine and we'll take a vote. Hi, what's your name?
I'm Sophia.
Hi, Sophia. Pleasure to meet you. So you're local?
Yes,
Uh,
I've been staying in Berkeley.
Are you a regular Berkeley student?
Yeah.
Great.
I'm in my second year.
Okay, so we'll come back. This is a tough one. You can change the camera shot. Oh, Timmy, you are on it. So we were displaying the board there. If you were looking at it, one of your classmates, Sophia, is here today, and she and I were just writing on the board. Come in to the lecture and write on the board with us during the chem quizzes. That's fun. And now we've got it set up that no one will see you, just your finger on the board. So what we have here is a situation. Let's first see what you're thinking in your voting. And green off metal 1 is very popular. And I agree with that. I think this one might be a homework question. You might have seen it already. I agree with that. And why is that? Well, first, the yellow. Yellow is not plotted here, but we know it's between the red frequencies and the green frequencies. So this is the rainbow spectrum: red, orange, yellow, green, blue, violet. So there's a mnemonic that some people use to Roy G. Biv. In fact, you can put an I in there. Roy G. Biv, somebody's name for the progression from red to violet. I for indigo in between blue and violet. So yellow, by that, is in here somewhere. And yellow photons will eject electrons from metal 1 with that kinetic energy, but not from metal 2. They don't have enough energy for metal 2. Is it the most? Well, green is going to beat them because green has this photon energy and it will eject electrons here. I suppose I have all this animation. And blue will eject electrons, but from metal 2 at this kinetic energy. So the highest is green off metal 1. Green won't eject any from metal 2, only the blue, the highest energy, highest frequency, will. I'm sure I have all that animation here. So there it is, a little more well drawn out. So the green there and the blue off metal 1 there. And in fact, the way we've drawn it here, blue off metal 1 is actually, or blue off metal 2 is actually the lowest energy. Highest frequency electron, highest energy photon, but lowest kinetic energy because it had to do this much work. This was all the potential energy you had to overcome. Overcome all this potential, and then the rest is kinetic. So the blue had more energy in the photons, but so much of it went into the potential energy of the metal and electron that it did not have a lot of kinetic energy left. Great, wonderful. So now we have two ways that we can explain and think about light. The wave nature, so it has a wavelength and a speed, and the energy is associated with the frequency or inversely with the wavelength, c being the speed of light. So we have this famous E equals h nu. Planck's equation, here we can write it, E equals hc over lambda. So that's that expression. But we're also saying it has a particle nature. And particles, what we use to characterize them are their momentum. Momentum includes both the mass and the velocity. The momentum is m times v, mass times velocity. So it's a handy parameter. We'll give it the symbol p, momentum, to give you an idea of what the particle is doing. And it's a vector because the velocity matters. It's a direction. So mass times velocity gives us this quantity towards momentum. It's handy for categorizing particles because they have mass and velocity. The issue is, and this is the sticky part, photons have no mass. They're light particles. So what is this? That's annoying that they behave so much like particles and they have this momentum they can transfer to a electron, but they don't have a mass. They have a relativistic mass, though. You could imagine what the mass would be, and you could use this expression. So I can write the momentum as the mass, and I got a little star there because we don't know what that mass is. It's a relativistic mass, but we do know their energy because it's their momentum is kind of because it's related to their energy. So you can write m times v or m times c because they're moving at the speed of light. And I could use then Einstein's famous equation, E equals mc squared. Now I can take one of the m's and the c's is momentum. So I can replace m times c with p times c. M times c is mc squared. So that momentum is in there, and that's still equal to the energy of the photon, hc over lambda. Now the c's cancel, and I see the momentum is related to the wavelength, just like we would have expected, because we expect the energy to be related to the wavelength. So that is kind of a remarkable result. That says that the momentum of these little particles that we can't see is dependent on its wavelength. And we had that feeling because its energy was dependent on its wavelength. So in the particle description, we say the momenta is h, Planck's constant, over the wavelength. How does that translate back to the wave condition? Well, just solve for lambda. The wavelength is Planck's constant over some momenta. So those are related. But here we see the wave particle duality of nature. So this is one of those mysterious parts of nature where the light, we can measure its wave properties in certain experiments, but if we do other experiments, its particulate nature shows through. It's acting like them both all the time. Wave, particle, wave, particle. Those are two manifestly different things. It's like it's like dessert topping, floor wax. you don't want to have both those things together at the same time. It's a dessert topping, it's a floor polish. You can see the commercial. Do we have a sponsor? No. No sponsors for that, but wave particle as kind of equally crazy as dessert topping, floor wax. So those two things related by Planck's constant and the momenta of the particle. Cool. Now we're starting to get into these weird parts of nature. So we've got to the tiny, and we already have this particle wave duality. So let me ask you this. A photon with 400 nanometer wavelength, so that's nanometers, 10 to the minus 9th meters, splits into two. It goes through here and splits into two photons. One of the two that it splits into is at 1200 nanometers, longer wavelength. What is the other wavelength? That one. Oops. Let me go back one. What is that one? I'll start the thingamabobber here. So you'll get a screen capture of that and talk about it. And I'll start my Zoom and pop into a Zoom room. Yes. All right, guys, take a stab at this one if you have not yet, and we'll see what you're thinking. All right, well, that's a representative number of you. Let's see. B is very popular. I'm surprised by that. I think a lot of these are appearing in homework, so you're this B is right. Let's not. I agree with the B's, but I tell you, I've done this many times, and it's rarely 50% of you get it on the first try. And Leo was telling me it also looked like the color code kind of told you, because this color looked like that color. Dang it. I'll have to change that. What I was trying to do was blue wavelengths, short wavelengths, yellowish wavelengths, middle, and red wavelengths, longer. That's what I was trying to do. And this one does happen to be yellow. So that's okay, but I shouldn't make it that obvious. Or maybe the color code. But so what are the B people thinking? That's the important thing. So the B people are thinking, oh, there, now see here, now it's quite yellow. And it's not, it doesn't match that. And it's numbered 1, 2, 3. So you can see my editing has been all over the map as usual. So wavelength is not conserved. One of the first things you could have said is, that's 400, that's 1200. Well, 1200 minus 800 is 400. That would conserve wavelength, but wavelength is not conserved. Energy is conserved. And energy, I have to take the energy of these two photons, the 1200 and this one that I don't know, and it has to add up to the energy of the 400 nanometer photon. So I can do that. And I've written the frequencies here, and I'm just noting that's the frequency of a 1200 nanometer wavelength. That's the frequency of a 400 nanometer wavelength. I want that frequency. Well, let's just write it as h over lambda. H over lambda, I can multiply through by c, of course, the speed of light, and divide through by lambda, and those are still energies. Hc over lambda, Hc over lambda, Hc over lambda. So that's fine. So the inverse of wavelengths are conserved. 1 over the wavelength is conserved. And then I can just do the fractions, do the math, get the least common denominator here, make that 3 over 1200. 1 over 1200 plus 2 over 1200 would give me 3 over 1200. So 2 over 1200 is 600 nanometer wavelength. Brilliant. That's the way to go. Oh, so we had trouble with box this morning, and I could not get to the next lecture. So let me see if I can find it now. It's so small that I can't even read it here. It must be there. And it must be there. So we'll get this one up, and we will start here and go. Okay, so now we understand diffraction and interference, and we understand quite a bit about waves. We understand that waves travel through space, and they have a wavelength and a frequency. And this is the wavelength. The frequency is how many times, if I'm standing here, a wave passes me per second. And we understand several other things about the waves. We understand that we can add and subtract them. So here's another wave, and this wave is doing that. So when I add these two together, I get no intensity, 0 intensity, because every high point here adds to a low point there, and that's destructive interference. These two waves cancel each other. They interfere destructively, and you get no intensity. That's how we get dim spots on our screen. And that happens to water waves too. If you're on a channel, you're out on the channel or out on the bay and you're watching water waves, and if there's some pair of openings, then the waves will go through them, but you'll get this pattern of peaks and troughs inside the harbor if one wave pattern is coming at the two slits, the two openings. So it's all kinds of waves. Doesn't matter if you're light. Constructive and destructive interference is possible. Here's the constructive interference. So if you interfere constructively, then these two add, and you get, running out of colors here, you get twice the amplitude. Okay? And we're saying that amplitude is proportional to the number of particles. Brighter light, more particles, and we're saying amplitudes and intensities correspond to probabilities. Okay? You can't have negative probability. So what we'll probably end up doing is we'll just take this function and square it. So everything is positive. So we'll say that the probability is proportional to the amplitude squared, just so we can get all positive numbers. We do this a lot in science. You've got something, you want to add magnitudes, you don't care, that being a negative magnitude doesn't help you. So you square things, and sometimes we take the square and then take the square root right back. Square it to get them all positive, take the square root right back to get the number we want to do. We want to have all positive numbers in magnitude. So we know this. We know one other thing. I could probably just erase this all in one shot. One other thing, and that is I can take, let's use a different color here. We can take waves that extend through space, and we can convert those from so here's the time dimension here, wave traveling in time. You could transform that into the frequency dimension, and we saw that you could do this thing called the Fourier transform. If you have a very good waveform, you can correlate the time dimension with the frequency dimension. So this peak at this frequency is the frequency of this wave. So in the time dimension, it looks spread out. In the frequency dimension, it's nice and tight, and you can read the frequency from a wave that's coming in if you plot the wave in time and do this mysterious thing called the Fourier transform. You don't have to know any of that math. It's just all waves. You can do that with all waves. There's a relationship between frequency and time. They're called Fourier transform pairs. You don't have to know any of that. It's just, I want you to know that mathematically, you can do that with waves. Okay, so that's a lot we know about waves. Here we saw the interfraction and interference patterns. So let's look at this now. Again, so we know if waves come in, wave patterns come in, they interfere, and on a screen here, you see this pattern of light and dark spots. Now, remember, you're picturing this in your head. This high intensity is just bright. Bright spot here, dim, bright, dim, bright, dim is what you see. So we have this idea, these waves behave like this. There's a wave nature, and we can detect it like this. We also know that waves have a particulate nature to them. But what would you have if particles hit? So you took particles and you went through two slits. Well, particles can't interfere. So this idea of the particulate nature of light is a little less clear unless we say maybe these are the probabilities of where the particles hit. But even so, it's crazy. If they really are just particles, the probability of where they hit, they should just come flying through here and bounce all over the place. And, you know, some will hit off the wall or off the edges of the slit. But if they're just coming through, what you should expect to see, and I think you would, you'd see a bunch of particles hitting here and a bunch of particles hitting here, because they can't interfere with each other. They're particles. There shouldn't be any place on this where a particle is not allowed to hit. You know, probability kind of 0 of seeing a particle hit there. That doesn't make sense. So particles coming through, we don't expect that to happen. But I think you're probably anticipating what I'm going to say. For some particles, they come flying through, but believe it or not, they stack up like this. The particles have a probability distribution on the screen, and it's not broad and they can hit anywhere. There are parts on the screen where you don't expect, you have very, very low probability. Very few particles hit there. There are some particles that do that. What kind of particles? Well, it looks like the particles are behaving like waves. So we have physical particles, electrons. That's a physical particle. No one's ever seen one, and we don't know how big they are physically, none of that. But we have this idea that we can measure their momentum and their kinetic energy. We have this idea that they're a physical particle. We can measure their mass. So they are a particle. But it turns out you can arrange this experiment and do it with electrons, and you get an interference pattern. And of course, when you're doing it with electrons, you don't see the dots. You see this bright and dark series. You have to do like with, you have to have a detector here that detects the beam of electrons. So bright spot on your detector, low, dark, bright, dark. When you do it with electrons. So we have a probability distribution, and we're going to associate, here's our wave equation that we had before, and we're now associating, as we know, the wave function, which is just a sine function. We're associating the square of that with the probability. Okay? So these are probability. Goodness. These are probabilities. I have to go back one, sorry, confusing myself. This is a probability distribution. I could take the square of the amplitudes of this wave function to get probabilities. So we saw with light, we had this duality. We could see the wave function, we could see the wave properties in the diffraction experiment. We could see the momentum, the particle properties in the photoelectric effect. So there's this duality where the momentum and the wavelength are linked. You could say to yourself, well, that looks like the same thing's happening here. I have an electron that's behaving like a particle manifestly. So we know it has a mass. We can measure the electron mass. But it looks like when it goes through that pair of slits that it's behaving like a wave. So what wavelength should I associate with this mass? Well, let's not associate it with the mass. Let's associate it with the momentum of the particle, because we know we could do that with light. So let's say this was the relationship for light, particle, and momentum. Let's just use the same relationship. Lambda is h over the momentum. So if I know the momentum of the particle, it has a mass and a velocity, I can calculate a wavelength. Is it right? I don't know. So far, this is just all supposition. We're just saying, what if you did that? What if you assumed matter behaved like light? You kind of saw it behaving like waves because it had that diffraction pattern. The particles Why not just apply the same thing that we derived for light? Well, it turns out it is true. Matter can behave like a wave. Now, that starts to get quite spooky because, I could sell you on the fact that the waves of light behave like particles. We even said you could dim it down until you could see the individual flashes. And we could see the photoelectric effect. Now, though, we have that experiment where the electrons going through slits, they're not actually slits, it's a grating, it's a crystal, but going through essentially spaces gives us a diffraction pattern. So the matter has this wave-like property, and we're going to correlate it just like we did with the light. Crazy property of matter now, we think. I want to go back. Oops. Stand by. First of all, we call these wavelengths, we give these wavelengths a special name. We give them the name de Broglie wavelengths. De Broglie postulated that matter could have wave-like properties. He couldn't prove it. He did some math. And it turns out if you just say, you write down some wave-like equations and some other things, talk about balancing momenta and energy, you could get a pseudo wavelength for matter. And he said it had this relationship, that we have this, the momenta is h over lambda. So anything with a momenta, you could calculate a wavelength. So baseball, here's a baseball pitched very fast at 40 meters per second with a mass of 170 grams. M times V is the momenta. You can plug it in, divide that into Planck's constant, and of course the wavelength is ridiculously small because the momenta is so big. So a baseball could have a wavelength, but it's so ridiculously small, 10 to the minus 26 nanometers. It's already 10 to the minus 9, and you're going, I'm giving these in nanometers, 10 to the minus 26 of those. So the wavelength is essentially a smaller division of space than we can even measure or conceive. The electron, though, when you get to these tiny particles, then the momentum gets very small. So the wavelength gets bigger, still not very big, 6 nanometers, 6 times 10 to the minus 9th meters, but on the order of the size of atoms now. That is something that we have a handle on, the spacings between atoms. Of course, the photon, their de Broglie wavelength is their wavelength. So there's a photon in the yellow, 600 nanometers, a electron moving at about 10,000 meters per second. So we can do a massive electron times that velocity, calculate 6 nanometer wavelength. Here's sodium atoms. So these are still small, and if they're moving 300 meters per second, relatively modest velocity, that corresponds to 880 Kelvin. So you know temperature, speed, velocity are linked. So this speed corresponds to about the particles at 80 Kelvin, pretty darn cold. But if you can get them that cold, that is slow them down so their momentum gets low, you can start measuring a wavelength. And this gets to the region where you can still measure 600ths of a nanometer. Now we're below 600ths of a nanometer, we're getting below the dimensions of atoms, but that's a wavelength you can still talk about in terms of scientific measurement. This one, forget about it. Okay, so I rarely do, as you know, I rarely do historical stuff in here because I don't want you to be distracted by the historical parts. Can we show just the screen? So you're going to see just the screen here. And the reason I'm doing this is this is a note taken around 1927, it was published, where Davidson and Germer, two scientists, they made a mistake in the laboratory, actually, and they shined an electron beam at a crystal surface. And they had it all set up to do with light. So actually, they were trying to measure the electron energies, but the crystal kind of got in the way. So the electrons went through the crystal by accident, aimed it at the wrong part of the apparatus. And when the electrons went through the crystal, their detector did this. Their detector gave them light and dark spots. They gave them a diffraction pattern. And here's what they said. This investigation was begun as a result of an accident which occurred in this laboratory in April 1925. And we must admit, the results have proved to be quite at variance with expectations. You can see it's from 1927. The results appear to be quite at variance with our expectations. We don't say that anymore. Right now, somebody would have written just WTF in their lab book. What the? So it's an electron beam, and he says it's crazy. It was striking this crystal, and we knew these spacings in the crystal. And since I knew the spacings, he could calculate what the wavelength would be that would give this pattern. So he did the calculation, and he said, oh my gosh, that corresponds exactly to de Broglie, P equals H over lambda. So out of an accident, they proved not only particles have wave nature, but it agreed with the previous mathematics that de Broglie was right. So that happens all the time in science, happy accidents. But this one is so funny and so beautiful that I thought I would show that to you. Okay, so let's do something here, laser cooling. So I want to use light. So now I know light comes in as particles, and I know particles are particles, and I know traditional particles, if they hit head on, they can stop each other, slow each other down. This momentum transfers to that momentum, and they go very slowly back in other directions. Slow particles down by, here comes a sodium atom, and I'm going to bang it with an electron beam till it slows down. That corresponds to reducing the temperature, slowing it down. So we call this laser cooling. I'm going to use light. I'm going to use the photons of light to bang into the sodium atom and slow it down. So about how many photons are needed to stop, or not stop, but slow down significantly the sodium atom if the sodium atoms start at 80 Kelvin and the electrons have the momentum of 10,000 meters per second that I had in the last slide. I'll bring that slide back up so you can see those numbers here. You have them. You can download the handouts, of course, but I'll start that so you get a screenshot of this. So there's the sodium atoms coming in at 80 Kelvin. I have those yellow wavelengths of light, and I have yellow photons coming in. Sodium atoms go this way. Those collisions, how do I stop that sodium atom? So there's the numbers you need to know and what we've been talking about. Talk about that amongst yourselves, and we'll see what you come up with. Okay. Leo, I should just introduce you to Sophia right here. You guys can just talk. You're sitting next to each other. Oops, sorry, my mic's on. So I'm just introducing Leo and Sophia so they can chat. They're actually sitting on the same couch, so it's easy. So go ahead and push your button if you have not yet. And we'll see what you're thinking. B and C equally popular, it looks like. So some of you thinking about 100, something you thinking about 10,000. So which is about right? Well, we saw a minute ago. Stop that. We saw a minute ago that we have sodium atoms coming in, and they have a certain wavelength associated with them. They have a certain momentum. The light particles have a certain momentum, and you want enough light particles, add up the momentum of each little light particle hitting the sodium so that in comes the sodium and particle of light slows it down to near a stop. So you need the momenta, you need a bunch of these so that the total momenta of all these cancels the momentum of this. You're kind of conserving energy, you're conserving momentum. So how do you do that? Well, set the two momenta equal to each other using their wavelength. The wavelength from the table for our sodium atoms is 0.06 nanometers. The wavelength for the photon is 600 nanometers. So this is exact. This I'm giving you a squiggly because that's an approximation. But I did it so the numbers are easy. So if these two things have to be the same, this momenta here, h over 0.06, is h over 600 times 10,000. So I need 10,000 particles that would add up to the same momentum as the sodium atom. And you could bring the sodium atom to a near stop. And you can do this experiment. You actually can laser cool. Some of the coldest temperatures ever achieved are using this technique. Taking lasers, you take a laser cavity. In concept, it sounds easy. In practice, of course, it's very difficult. But you can trap some sodium atoms in a laser cavity and tune it so that they're smashing into each other, continually slows the sodium particles till they get to a ridiculously low temperature, tenths and hundredths of Kelvin degrees. Steve Chu. God, why couldn't I think of his name? He was sitting right here a couple of days ago. Stephen Chu won the Nobel Prize for this, and he was sitting right here in this desk, right pre-COVID. He came to give a talk on a very prestigious talk here at Cal, and we let him, said, here, use this office, chill. We can shut all the doors and windows because he's visiting almost everybody on campus. But he needed, give me a half hour before I talk just to, chill and get my thoughts. So he sat here. We had lunch in the conference room. Steve Chu, as you know, was the Secretary of Energy, Nobel Prize winning Secretary of Energy for President Obama just a few years ago. So Nobel Prize winner, Secretary of Energy, did this experiment. He was at Cal for a while. He was here. He's now at Stanford. Poor bastard. But he came over here to give a talk. We had a great chat. We had a great lunch. And he gave one of the most amazing physical chemistry talks I've ever seen in my life. He's going to win another freaking Nobel Prize. You're going, what? Oh my God, that's a good idea. He's one of those guys like Einstein. Has a good idea. Well, if these particles and these photons have momenta, shouldn't I be able to bounce them into each other and stop that and then realize it as a very low temperature? Yeah. Nobel Prize, man. Okay, so let's do this one together. Electrons with a wavelength around 400 nanometers are heated to 4 times their kinetic energy. What is the new lambda? So I'm going to increase the kinetic energy of the electrons. Kinetic energy is 1/2 mv squared. We saw that earlier. This is what gives you temperature in systems with moving particles. You could write the kinetic energy in terms of the momentum then. If you take mv, square it, so you have m squared v squared on the top, divided by 2m, then you have 1/2 mv squared again. So you can write energies in terms of momenta. That's why we can transfer those energies as momenta and slow down those particles. So if you heat it to 4 times their kinetic energy, so we do this, we're talking about in terms of a temperature again, get it hotter, going faster. What is the new wavelength? So how does their wavelength change? Well, first, we can probably maybe throw out one of them. If we're going to higher kinetic energies, that's higher momenta, the wavelength is inversely proportional to the momentum. So bigger momentum, it's going to go to shorter wavelength. So the longer wavelength one is out. What is the actual number? Well, here's the kinetic energy. For constant m, we have just one kind of particle. We have all electrons. So constant m, the kinetic energy is simply proportional to the momentum squared. So just write the two momenta. To get to 4 times the energy, I have to square the momentum. So if I took 2 times the momenta and squared it, I would get, well, it's not super obvious. Let me just write one more thing on there. If I write 2 times the momenta, that equals 4 times p squared. And p squared is the kinetic energy, goes as the kinetic energy. So 2 times the momentum goes 4 times the energy. So I get a reduction in a factor of 2 in the wavelength from a factor of 4 in the energy. You can do that math, take a screenshot of that if you want. Okay, we're catching up. Oh no, I have to go get the next one. So sorry, guys. So one thing we have today is we have this new camera and this fancy switching thing we're using. And we were spending some time getting that set up, and I forgot to stitch all the lectures together so that they would come in smooth packages. You can see what I do. Each time you see a lecture complete, that's where we would have stopped in the 50-minute lecture in Pimentel Hall. But of course, we have to keep going because we have to do everything twice as fast. So matter waves is next. Light particles, matter waves, uncertainty is what we just did. So we need to go to quantum in 1 dimension. So let's go there. Sorry about that, guys. So we'll continue on. We've talked about now all these properties of waves. We were able to add them up. We were able to subtract them. We were able to do this constructive and destructive interference. We know their intensity is related to the number of particles. So it's a probability. And we're saying the intensity squared will give us a probability of finding the particles. How many particles are there? So what we're doing, everything we've talked about is just waves still. Before there was quantum mechanics, before there was this whole wave particle duality, before any of that, all these things were just properties of just plain waves. Waves mathematically have all these properties. So the origin of what we're going to talk from now for another week here, the origin of everything we're going to talk about now is just those experiments were done where people said, oh my gosh, matter has wave-like properties. So people all over the world just started scrambling and taking everything we knew about waves and applying it to matter and to see what would happen. So a natural progression of things. We know so much about waves. You know, the Fourier transform, we know destructive, constructive interference. We know intensity, we know probabilities. So let's just apply it to matter. So first, a little bit more about waves. So standing waves. So far, we've had traveling waves. We can see standing waves. So a standing wave, I might be able to get one here. Tell me what this shot looks like. We could have composed this shot. Oh, you know what we can do? We can be really fancy. We can have like preset 1 and preset 2. So preset 2 is the is the expanded shot. Just talking to our producer director, Sydney here. So is this visible? Can you guys see this? So here's a string tightly. And you know you can, we were doing this with the blue cloth. You could send a wave traveling along it. It'll go from there to the end. But you can also do this thing where you know this. You could do jump rope. And you could get, come on, jump rope. Oh, well, let's just stop there. What does that look like on the way? Can you see two humps? You can see 2 humps. That's kind of cool. There we go. You can see 2 humps. There's 3 humps. I don't know if you can see that one as well. But you can see, there's a traveling wave. I can get it. Look at that. 3 humps standing. That wave's standing. That one's not moving. Sophia, can you stand up and point to where the wave is not moving right in the center? Don't touch it, but just show with your finger. Yep, turn around, face the camera. Say, there it is.
There it is.
That is where the, thank you, Sophia. That was where the, you'll have to sign a release. So that is where the rope wasn't moving. So the rope was moving crazy fast, but then where the wave intensity went to 0, the rope was not moving slowly. So all that energy on the wave, but parts of it that were quiet. And the wave wasn't moving. You could see just oscillating. The intensity is going up and down, but in a specific place. So we call that a standing wave. So how do standing waves then apply to what we've been talking about? Well, first, how do you get a standing wave? You get a standing wave when you put boundaries on your waveform. So if I'm shaking the string up and down, I can get a wave to travel, but how do I get them to just stand and sit there and not move? Well, I have to arrange it so that there's an even number of half wavelengths. 1 half wavelength, 2 half wavelengths, 3 half wavelengths. Essentially, so there's a 0 point at my hand and a 0 point over at the wall. I can't have it hit the wall at an energy point. The wall has to be a 0 point, and my hand has to be a 0 point. Those are called boundary conditions. And if you take nothing else home from Chem 1, take home the fact that if you have a wave phenomena and you slap specific boundaries on it, say you got to start here and stop there, you get a natural phenomena known as quantization. And again, that's just a wave thing. We've known this. Here, I'll show you another one. Sound is waves. So here is a tube of a fixed length. So if I'm going to have sound waves, then I'm going to have to create waves such that they have a 0 here and a 0 here, but they can't have zeros along the tube as well. So if it's sound, what does that mean? Well, you're going to have one wave that does that, 1 full half wavelength. That'll have a frequency that's relatively low. You could have a node in the middle, a 0 in the middle, and a full wavelength standing. Or the one we saw, 3. High intensity, 0. Low intensity, 0. High intensity. But it's sound. So that low frequency, higher frequency, and higher frequency are the only ones that fit in this tube. So let's listen to them. Three waves. The sound didn't go whoop continuously. It went ah. You recognize that. Bum, bum, bum. Those are the fundamental frequencies of a string. Those are what's that space oddity? Bum, 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 ba-da. Those first three notes are the fundamental. It's a space oddity. It's about the fundamental nature of the universe. The first three notes are the fundamental vibrational frequencies, the fundamental waves that fit on a fixed length. So not every frequency is allowed. Specific frequencies are allowed. That's cool. There's this allowed thing. There's this weird quantization. There's only certain energies because there's certain frequencies allowed on a fixed wave. If you're traveling through space, any energy. We saw kinetic energies of electrons, they're waves, but if they're traveling through space unbound, they can have any kinetic energy. Stuck in boundaries, only certain energies. So let's look at that a little more. I'm just going to define here the physical system we're going to look at. We're going to take now a mass rather than a manifestly wave property. We'll take a particle property. And what we're going to do is set boundaries on it. So we'll say, well, let's say we have a very tight string and a bead on the string that can move back and forth like that. And we want to describe the position of that bead going back and forth. And the box that we fix it in, the length of the string will be L. So our x-axis will go from 0 to the length of the string, L. But let's treat it not as a particle moving back and forth, but as a wave. So let's give it a wave function. Here's our wave function, just our generic wave function again. And we know, and we call them capital psi now is the term we're giving to wave functions. Capital psi is a function of x along the x-axis is a sine function. And we came up with this constant times x, 2 pi over lambda times x, where lambda was the wavelength of the wave. That's how you would plot one out. And this could be a traveling wave. We haven't really fixed it in space yet, but this is just a generic function for a wave. So what we have to have are what we call boundary conditions. At this psi equals 0, this point, the wave function has to go to 0. And at this point, L, it has to go to 0. Those are the two boundary conditions. Psi of 0 has to be 0 and psi of L has to be 0. So if you plug in L for x, you better get 0. If you plug in 0 for x, you better get 0. We know that's easy to do because we know the sine function oscillates between +1, -1, and 0. We're just fixing the points. So let's look at how that evolves quickly, just in pictures. We saw already we could get half a wavelength, solves that. A full wavelength solves 0 at both ends, but introduces a 0 in the middle. And 1.5 wavelengths worked. 0, 0, but now 2 zeros in the center. Boom, 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 ba-da. Those are the fundamental frequencies. Now they're the fundamental frequencies of matter if our matter is behaving like a wave. So we've trapped a wave in this box. So there we go. Half a lambda, a full wavelength, and 1.5, 3/2 wavelengths. So we can do some math then. We can say, well, the length of the box is L, and it looks like n, where n is an integer, times lambda over 2 are the wavelengths that will fit. So this is the relationship between the length of the box and the wavelength. So you can have L is half a wavelength, L can be a full wavelength, or L can be 1.5 wavelengths. So I can write that down, and those are the ones that can fit only integer values. You can't have non-integer values. You'll have integer values fit in here to get this. So we can see quantization. We can call these quantum numbers. You can have this energy, or this energy, and none in between. We'll stop there because that's a fundamental thing. Totally cool property of matter now, as well as just waves, and we'll develop that further tomorrow. All good? Clear? Fantastic.